Maxwell distribution gives us the distribution of speeds for molecules in a gas. And so the frequency of a particular speed is given by this expression. So it's 4 pi v squared, the mass of an individual molecule, over 2 pi kt to 3 halves times e to the negative mv squared over 2 kt. And so remember, this is a molecular, not a molar mass. So some number on the order of 10 to the negative 26 kilograms. And Boltzmann's constant, of course, 1.38, 10 to the negative 23rd joules per Kelvin. It's also equal to the gas constant divided by Avogadro's number. Okay, so looking at this, we can see that there's really two parts to this. This is a rapidly decreasing function of speed. On the other hand, this is an increasing function of speed, so we should expect something that has a maximum in it if we graph it. Let's go ahead and graph that. If we graph the Maxwell distribution, we get the frequency of any particular speed as a function of speed. And what we get is something that's like a very, very skewed bell curve. Okay, and we look at this, we can see that we could call this the most probable speed. And then we could also take several other types of average. We could have an average speed, which would be the RMS speed, root mean squared, which is taking the speed, squaring it, then taking the average, and then taking the square root. So root, mean, square. Of course, we could find the most probable speed by taking the derivative df dv and looking for this maximum. And if you do that calculation, you get the most probable speed is going to be 2 kt over the mass of the molecule. On the other hand, the RMS speed is going to be 3 kt over the mass of the molecule. Somewhere between there is the average speed, the average, and that's equal to 8 kt over pi times the mass. It turns out that the most important of these speeds for us is going to be the RMS speed. And the reason for this is that kinetic energy, which is the most important form of energy for an ideal gas is the only form of energy, is going to be proportional to v squared. So that's why the root mean square speed is the most important speed in characterizing the behavior of gases. So from now on, when we talk about the speed of gas molecules, we know that in a particular sample, some molecules are fast, some are slow, but we'll just be referring to the RMS speed when we say the speed of molecules in a gas.